The year 1763 witnessed the posthumous publication of Reverend Thomas Bayes' an essay towards solving a problem in the Doctrine of Chances, a work that, despite its seemingly modest title, would profoundly reshape the landscape of probability theory and statistical inference. The essay's central ambition lay in addressing a critical limitation of the then prevalent understanding of probability, specifically the frequentist approach. This classical view, rooted in the principle of equally likely outcomes, struggled when confronted with the challenge of inferring the probability of a cause given evidence. Bayes, a Presbyterian minister and a man of profound mathematical curiosity, sought a method to navigate this critical gap, providing a framework for reasoning under uncertainty. The immediate intellectual context reveals a scientific environment grappling with the nascent field of probability. Figures like Blaise Pascal, Pierre de Fermat, and Christian Huygens had laid the groundwork, focusing primarily on predicting the probabilities of future events given known parameters. The challenge, however, resided in what Bayes termed the inverse problem determining the probability of a past event or cause, given the observed outcome. This question held immense practical implications in fields from astronomy, where scientists sought to infer the positions of celestial bodies based on observational data, to jurisprudence, where the likelihood of guilt needed assessment based on evidence. Bayes' essential contribution lay in formulating a method for updating beliefs in light of new evidence, a process we now recognize as Bayesian inference. The core question he posed was deceptively simple given an observed effect: what is the probability of a specific cause? To tackle this, Bayes introduced the concept of inverse probability, a methodology that sought to reverse the conditional relationship that defined probability in its classical form. He posited that, prior to observing any evidence, one should assign an initial probability to the cause, or prior. Then, upon observing the evidence, Bayes provided rules by which the priorly updated yield a posterior probability, representing a refined. The essay's immediate impact, despite its delayed dissemination, resided in its radical departure from traditional probabilistic thought. The core tenet of Bayesian inference introduced a subjective element into the assessment of probability. The approach considered degrees of belief. By assigning probabilities to hypotheses, Bayes offered a way to incorporate prior knowledge, experience, or intuition into the process of inference. This stood in stark contrast to the objective frequentist approach that relied exclusively on observed data, thereby limiting inferences to statements about the relative frequencies of event occurrences. Bayes' essay was a meticulously reasoned work. He used carefully selected examples to guide the reader through intricate mathematical arguments. The essay demonstrated several key mathematical steps, beginning with clearly defined assumptions concerning the probability of events. The essay introduced a conceptual framework where probabilities could be thought of as distributions, not just single values. As an example, he described an experiment where a ball is thrown randomly on a surface, and observing the position of the ball becomes the evidence. A probability distribution describing the ball's location provides an initial distribution, or the prior probability. This prior then gets updated or modified given new evidence of the ball's location. The significance of this framework extended beyond its immediate mathematical implications. It laid a conceptual foundation for a fundamentally different way of thinking about how we learn and make decisions under uncertainty. For Bayes, the process of inference was a dynamic one. As new evidence becomes accessible, beliefs should be continuously updated. This viewpoint revolutionized how philosophers and scientists addressed questions involving the unknown. The essay, though initially published anonymously, was published after Bayes' death by his friend Richard Price. Despite its relative obscurity at the time, its potential was eventually recognized. Its influence resonated slowly, but its seeds were sown. The essay's ability to incorporate prior knowledge and update beliefs based on new evidence marked a pivotal moment in the history of science. The essay, therefore, serves as a testament to the power of mathematical reasoning to extend and refine, shaping the trajectory of human knowledge. The core of Bayes' contribution, presented in his 2763 essay, centers on solving a problem in the Doctrine of Chances. The problem, in its essence, asks how one can infer the probability of an event, given prior knowledge and new evidence. Bayes addressed this through a carefully crafted mathematical framework, built on a foundation of conditional probability. Bayes' work begins with several key assumptions. He posits that outcomes are independent and identically distributed. This means each event's occurrence does influence further events. The probability of any individual event remains constant across observations. He also assumes a uniform prior distribution for the unknown probability. This is belief that all possible values of the parameter are equally likely before considering observed data. This initial assumption is pivotal. It establishes a reference point for updating beliefs. The heart of Bayes' solution sits in his theorem, which provides a formula for updating beliefs in light of new evidence. Bayes' theorem, as presented in the essay, operates as follows. Consider the probability of event A given event B. The theorem states this equals the probability of event B given event A times the probability of event A divided by the probability of event B. Mathematically, it is stated as the probability of a given B equals the probability of B given A times the probability of A divided by probability of B. This formula encapsulates the essence of Bayesian inference, allowing for the updating of probabilities based on new observational data. This is the cornerstone. Bayes then applies this theorem to a specific scenario. Here, he considered an experiment that resulted in a series of successes and failures. The goal was to infer the probability of success for the next trial. Bayes elegantly used the beta distribution as a prior distribution. This choice of a beta prior is crucial. It possesses the necessary mathematical properties. The beta distribution is flexible. It can assume various shapes. It is always defined for probabilities between 0 and 1. Critically, when combined with a binomial likelihood, it produces a posterior distribution that is also a beta distribution. This conjugate relationship vastly simplifies the calculations. Bayes' proof involves several steps. First, he defined a binomial probability. Next, he expressed the probability of achieving a specific number of successes in a series of trials. Utilizing the uniform prior, the posterior distribution is determined. The end result illustrates how prior beliefs, represented by the beta distribution, are updated. The posterior, reflecting the revised beliefs, is determined by incorporating the evidence from a set of trials. The theorem's utility lies in its ability to update belief, converting prior knowledge into the posterior probability. The were, at its time, received criticism. The selection of the prior became a point of contention. Critics questioned an objective process of selecting prior probabilities. The essay did not specify what constitutes a truly objective prior. This debate, however, did not diminish the significance of the theorem itself. It stimulated methodological development. The immediate impact of Bayes' work was not widely felt. It was posthumously published. Nevertheless, the framework's potential was recognized over time. Pierre-Simon Laplace independently derived and extended Bayes' work. He developed a far more sophisticated understanding of Bayesian methods. Laplace's contributions, published in his Theorie analytique des probabilités, expanded upon Bayes' ideas. He applied them to astronomy and other scientific applications. Together, both men significantly contributed to the development of probability theory as a central component of scientific inference. The legacy of Bayes' theorem is profound. It extends far beyond the initial problem of inferring probabilities from observations. It has found applications across various fields. Machine learning, particularly in Bayesian networks, employs the theorem for probabilistic reasoning. Artificial intelligence uses it for decision-making under uncertain conditions. Medical diagnosis uses Bayes' theorem for disease diagnosis. The theorem's influence is evident in modern probability and statistical analysis. The implications of Bayes' theorem are significant. Extending into the realm of philosophy, it challenges the traditional understanding of knowledge acquisition. It highlights the dynamic nature of belief. Beliefs should evolve based on evidence and the incorporation of new information. The theorem does not merely provide a mathematical tool, it encapsulates an epistemological methodology. It emphasizes that knowledge is provisional, subject to revision. It underscores the scientific method as a process of iterative refinement. Bayes' theorem continues to influence our understanding of uncertainty, evidence, and the very nature of scientific inquiry.